Hey everybody, we're going to be looking at section 17.2 in this video, which is called line integrals. The um, the book makes this sort of wry observation that these shouldn't even be called line integrals. That implies you're integrating along a line, but in fact, what you're doing is integrating along a curve. So maybe curve integrals, although I guess it's a moot point. The way the world talks about these things now, they're line integrals. And I want to show you the sort of granddaddy of all reasons to look at line integrals. It's the operation of, this is the animation I'm about to show you is the standard internal combustion engine, a four-cycle engine with intake, compression, firing, exhaust. Those things happen one after the other. Each stroke of the piston, actually only one out of four of them is doing any work. The rest of them is just prepping or, bringing the fuel air mixture into the cylinder, compressing the fuel air mixture. That's actually sort of doing negative work. The engine needs to do work on the working fluid to do the compression part and then exhausting it out. But the one that's doing work is when it's turning orange in here. You see the flames come on, and that's where you're really pushing the piston downward by the expansion of those hot gases. Right. So let's switch to a drawing mode, and I'll try to make clearer what the issue is. Um, You have in the power stroke of a engine of this sort, the the connecting, what is this thing called? The way the connecting rod attaches to the crankshaft is a point that moves in a circle as the crankshaft goes around, right? And when you're at what's called top dead center and the fuel just gets ignited, the piston is applying a straight up and down force on you, which is kind of bad because the 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 connection point is moving sideways and the force is happening straight vertical. There's no work being done when your force is not passing through a distance. But a little while later, you're at a spot, say here, and that force now is acting at an angle. It's not vertical anymore. And that angle gets most severe when your point in motion around the crankshaft is as far out as the, sort of the 90-degree spot. So then we'll have a large force applied at a rather sharp angle. The angle gets less again, and it's actually straight up and down again when you're here. So I don't know if these vectors are slanted enough. This one should be the most slanted. This one and this one only a little bit slanted. And really, of course, there's a continuous motion of uh, positions along this circular arc and forces there. Now, we should look at what that means when we actually integrate differential work in order to get work along that path. So I mentioned previously, at first, our displacement is a little sideways thing. Later, the displacement is at some angle. Over here, when the twist of the twist is the wrong term, the angle that the connecting rod is at is the largest. That's when our displacement is straight up and down. And then the displacement goes back towards, well, actually, eventually going the other way. Now, you should notice that these dot products, the red force with the black displacement, in this position, that's going to give you a zero because those two vectors are at 90 degrees to one another. But here, there's a dot product. These two vectors are pointing in the same direction. I don't know how much that is, but there's some amount of positive force times distance happening there. And there's sort of a large amount of force times distance happening here. It gets smaller again, and then it goes to zero. So if you look at the work that's being done there as a Riemann sum, I'm doing a Riemann sum with what, 5 parts? It's 0 plus something bigger plus 0 again. If you want to see that as something where we might divide things up more finely and go to a higher order Riemann sum, and then eventually go to the limit and you'll get an integral. Well, that's going to be total work, right? We're seeing an integral in some sense of a force dotted with a displacement. It turns out this is with respect to arc length. That's how we're going to do that. But think about what's going on now. We've got a space curve, this circular or semicircular arc, and then we've got a vector field, these red vectors. And we're combining those two, dotting the red vectors with the displacements along the space curve. In fact, displacement times ds, that's really your velocity vector along the space curve. Am I saying that right? Well, it's something akin to velocity. It points in the same direction as velocity. Um, yeah, so this is the kind of thing we want to actually be able to do an integral of and find out how much work is performed on the piston, pushing down on the connecting rod and having that work translated into the crankshaft on an engine. The general case here is what I like to call integrating a wavy wall. So that terminology deserves some explanation. This is one example of many you can find out there. Apparently the expected or accepted term for these things is a crinkle crankle wall, but you will see these kinds of walls where the bricks are laid out in like an S curve in all kinds of places. The University of Virginia famously has a whole lot of these wavy walls. You see them a lot in the United Kingdom. So it requires some explanation. Why would you make a wall be wavy like this? Well, the problem comes from just trying to be economical. Apparently, there was a large tax on bricks at some point in English history, and so you'd like to make walls that had a single brick's worth of width rather than two or three, which is the more standard thing. But if you make a wall that's only one brick wide, it's trivial to push it over. It'll just flop over. It's not wide enough to support a horizontal force. But if you also make it have a path that wiggles like this, well, now you won't be able to force it over. And that's the idea. You can use fewer bricks. It's not exactly half as many because you're going to use extra because they're in this wavy pattern, but still you use fewer bricks in making a curvy wall that is one brick wide than you use in a straight wall that's two bricks wide. So they're trying to be economical, yeah. But the main reason here is this is a great visual for what the kind of integral we want to do is. Um, so I should go back to the drawing thing and we will see that. I want to give you two perspectives on such a wall. One is bird's eye view. You might have a wall that follows along some curvy path like that. Starts at a point A down here, ends at a point B up here. And I'm making it look like maybe a sine curve, but it could be any kind of not straight line there. But if you see that in plan view now, um, and this is in contrast to the way these actual brick walls look like, you might have some sort of function that gives the height of the wall. Trying to draw it so it still looks wiggly along the bottom, but it's also wiggly along the top. Yeah, so that's what we're trying to work out is in a Riemann sums way of thinking about it is how many bricks are there in this wavy wall which also has a wavy top. And what's the wavy top? That's generally going to be the height of this is the scalar you get out of dotting a force and a displacement. That's that's the y coordinate there. The position along the curve, that's arc length, right? So you want to take this wavy looking thing that's got a wavy top and sort of pull it tight and lay it out straight, and you will now have a Calc 1 integral, right? This is if you've taken the waviness out of that, you've just looked at things with respect to arc length. Now here, and whatever this function is ends up being on top, you just need the area of this to get you, well, if you're really doing f dot d, this area is going to give you a work computation. So here's a Desmos screen with an example of the kind of thing we're just discussing. What I have here is something that, well, if you look on it straight down from above, it looks like just some path in the XY plane. It's excuse me, it's wiggly because of the way I chose the path. But there's also, let me change the path, turn that part off and give you the surface. There's also a z as a function of x and y thing involved here. So I've got a surface. This is actually kind of the 2D version of a bell curve, the Gaussian function, although shifted up in the air a little bit. So it's 1 plus a Gaussian. But if I draw the stuff that's under that curve along the green path that I was just showing you a minute ago, you get this thing. And this is a thing with a curved cross section seen from above and a curved cross section seen from in plan view. And we'd like to know how much area is in that curved thing. And it really just does come down to pulling it tight and straightening it out and integrating with respect to arc length along the curve. Yeah. I hope that visualization will help with thinking these things through. All right, well, here's the a little of the text at the beginning of the section 17.2. The first thing you'll notice is they've just given us the definition of arc length along the curve. You integrate from the start of the curve to t, the length of r prime, the velocity vector. And that's done with respect to sort of an artificial variable u, because we're using t as the upper limit of the integral. I feel like that's a little bit artificial. In the book, what they're doing here now is saying, all right, differentiate both sides of that, and you'll have s prime on the left, and differentiating just peels off the integral. So you end up with s prime equals r prime's length, which is what they've written right there. But maybe it's more straightforward. Let me change view here. Maybe it's more straightforward to say this. The quantity ds dt, that is how fast arc length is changing with respect to time. That's speed. So that is indeed the length of r prime. And you can turn this in by just treating the Leibniz notation kind of the way it's meant to be used as as fractions. You can solve for ds. ds is equal to the length of r prime times dt. By the way, that's actually relating to differential line elements by a Jacobian determinant. Okay, that's an example of what happened in the last section, well, 2 sections ago. But still, it's really just saying that the relationship between how we measure arc length in the true arc length direction versus how we measure it as if where time is sort of filling the role of distance along the curve. The scale factor between those two things is simply the length of the velocity vector. Okay, so then what else do we learn from here? Um, the kind of integral we're doing is called scalar arc length or a scalar line integral. It's the symbol here is an integral sign with a C underneath of it. Often that C is done as a sort of curly letter because it's the curve. We're integrating along a curve some function with respect to arc length. Now here they've made that all those pieces a little more explicit. The, the curve is determined by these two parametric functions, x of t and y of t. And as t passes from a to b, x of t and y of t traverse the curve we're interested in. So t is the variable in this integral. Beyond that, what we have is the length of our velocity vector dt, which we've just said was ds. So this is f at r of t with respect to arc length. Except that you'll notice that while it's really being we're doing the particular integral we're looking at in order to think of this as an arc length integral. In fact, if you notice, everything is a function of t, x of t, y of t, r prime of t, dt. So we get to do a time integral that gives us the same result as an arc length integral would give. Here they're just saying, I don't know, the same stuff again. Sorry, my phone is giving notifications that it didn't mean for do. Sorry for the interruption. Yeah, so f of x of t and y of t, that is in fact our scalar function's height at a point along the curve. With the square root of x prime t squared plus y prime of t squared. Yeah, that's the length of r prime dt. This is the form of the kind of integrals that will give you the area of one of our wavy walls. I think we better do an example. I don't like that example. You can return to that if you want. Do I have another example? Wait, I think it's in the next section. Yeah, this is example 2 is an example that I think is worthwhile for us to go over. So I'm going to transition to where I can make drawings again. The integral that was given there was the integral along some curve. See, I try to make my c's look fancier. Of xy plus 2z It's weird that that has all three variables in it with respect to arc length. Oh, well, because this integral is happening in R3. That's why it's got all three variables in it. Well, I don't think that's going to change anything. We're going to let C be the line that goes from 1, 0, 0 to 0, 1, 1. Right. So first we need to give a parameterization of that line. Let's see. I would like my position function along the line, function of time, be first start at 1, 0, 0. Let's write it as a vector. and then march along in the direction the vector that goes from one of these to the other. Now that's going to make it so that as goes from 0 to 1, we'll start when t is 0 here, and we'll end at t is 1 at 0, 1, 1. So what is this vector that's going to be next to multiplied by t going to be? It's the difference between these 2 points. So let's see. I want it to be minus 1, comma 1, comma 1. Let's just double check. What is r at 0? That's clear. That's definitely going to be t is 0. That part's gone. That'll give you 1, 0, 0. What is r at 1? Well, 1, 0, 0 plus 1 times this thing. And when t is 1, we'll get in the x-coordinate 1 minus 1. That's 0. In the y-coordinate, it'll be 0 plus t times, plus 1 times 1. That's 1. And in the z-coordinate, 0 plus 1 times 1, also 1. So you see as t goes from 0 to 1, the position is going from the first point to the second point. That's just a check on whether we got the parameterization of that line right. Okay, so what's r prime? In fact, we guess we want the absolute value of r prime, but turns out it's positive anyway. R's derivative, when you take a derivative with respect to t, the constant vector goes away, and we've got our variable times another vector. That's just the t turns into a 1, and you get just this vector, minus 1, 1, 1, except we're looking for the length of that vector, which is what? Root 3. Is everybody quick enough to see that that should give you root 3? When you square each of these things, you get 1. Add them all up, you get 3. And square root that, you get root 3. It may help for us to sort of spell things out a little more. The I gave this r of t previously, right here, but r of t is really 3 separate parametric equations. We have a x of t, which is the x-coordinate of our point, which is going to be 1 minus t. You run through what r of t's work is. Y of t, what's the y-coordinate of the r of t vector? Sorry, it's over here. 0 plus t. Oh, that's just t. And z of t. I think that's also just t. Right? You have a 0 plus t times 1. So those are our positions, and we're going to plug those into the formula that we're, the function, the scalar function that we're integrating. So x and y, let's go back here a little bit and see what we're looking at. The thing to be integrated is x times y plus 2 times z. So that's going to be, I'm going to still say integral over c, but we're actually almost ready to do this in terms of arc length now. The x-coordinate is 1 minus t, if we're on the curve c. The y-coordinate is t. And the z-coordinate is also t. And we are going to need to integrate that with respect to arc length, but that happens to be root 3 times t. Sorry, shouldn't have said it that way. It's root 3 times dt. Now, I have a good feeling that a lot of this is going to simplify. we get a 1 times t minus a t squared plus a 2t. That's no, t, 2t, that's 3t minus t squared, isn't it? So it's that thing. The differential on the end is root 3 dt. And really, I don't have to use this artifice of saying it's the integral over the curve C anymore, because this is all done in terms of the t parameter. So what range of values does the t parameter pass through as we move along the curve? Well, this all was designed to happen so that we went from t equals 0 to t equals 1 as we move from one point to the other. So rather than having this c down here, I can just say this is an integral from 0 to 1. And it's with respect to t, right? So that it makes sense that those are t limits. Right, so now we can just, that's calc 1 from there. We can do the integral. Right, so that's the kind of procedure you're going to follow in general. Find a parametrization of the curve, plug that parametrization into the function that you're integrating, work out what ds is. It's okay, it's just speed times dt. And then you'll, once you've subbed everything in, you should end up with something that's really just an integral with respect to t. It's as if you're doing something in your Calc 1 class. Well, much as that may have seemed kind of complicated, that's the baby steps version of the stuff we're looking at. Because what we were doing in the end was integrating along a curve a scalar function. Well, we really want to find out what goes on when we have vectors in this position. How do we integrate a vector field? Well, you can't just integrate a vector field. You have to have something to dot it with so that you get a scalar. So it will reduce, it will reduce to the sort of shape we've just done. That is, we'll have a scalar, but that scalar will come from dotting two vectors. Let's take a look at the text here. So what are they saying here? Well, first of all, let me point out, actually, darn it, I have to go back. But it's worth going back because we want to make this point clear. When I integrate along my wavy wall with respect to arc length and get the height of the thing, getting the area of that wavy wall, it kind of doesn't matter whether I worked from this end to that end or vice versa. And the main reason that it doesn't matter is because we used absolute values around r prime here. We're just working on speed, and we're not caring about its direction. So that changes when we have vector fields to deal with. We have to be very careful about the direction of our curve that moves us along the wavy wall. So they, I love it when they say this kind of thing. Recall that. I don't know that we've ever talked about that before, so it's weird for them to say recall. But an oriented curve is a parameterized curve with a direction that's specified. Generally, the direction where the parameter increases is called the positive direction. So the last parameterized curve I did a minute ago was t going from 0 to 1, me moving us from one point to the other. That line had a direction on it. You start at the 0 end and you end at the 1 end. We got to watch out that we really take the direction of the curve into account. When we want to do a line integral of a vector field along an oriented curve, Well, the vector field isn't so bad. This is a function of x and y, and you just plug in the x of t, y of t. Or if it's in three variables, f will be a function of x, y, and z, and we'll have to plug in x of t, y of t, and z of t, so that we turn our parameter into three components and then plug them into the vector field and get another triple of components, a vector, at that position. We're going to look at, this is important, this is the tangential integral. That is the line integral for the tangential component of f. That has a lot of applications that are real, most importantly, calculating work and energy. So what's the ingredients here? You have a curve C with a R of S in it, right? I think we're going to want to say R of T in a minute, but still the X, the Y, the Z coordinates are all functions of arc length along the curve. And F is a vector field, just arbitrary, right? Any old vector field that's defined on a region that contains the curve C. So look, at each point of C, there's a unit tangent vector. That's something we've done previously when we did space curves. And that gives you the direction. That means, you're going in the positive direction along the orientation of C. What does this mean? The component of F in the direction of the tangent vector. Well, they're saying it's the length of F times cosine of theta, but it's really easier to say what it is in terms of a dot product. It's the dot product of F and T. So this little graphic here gives a nice example of what you should think about. First of all, they've got a curve just drawn in space. It's passing through 4 points, but that's not so big. You can first draw just position vectors along the curve. There it is, the position vector for P1. Here's P2, P3, P4, back to P1. It's just moving us around the curve. We should also look at tangent vectors. So when the position has us at P1, you see the blue tangent vector is moving in the direction of the curve at that point. Here's the same pair of things at P2. There they are at P3. Oh, I didn't know it would move like that. And finally P4. Well, I'm sorry if that was disorienting when I moved the graph around. Now they've got some buttons here that I think I need to turn those things off. Okay. You can show F on C. F is a particular vector field. It doesn't matter what it was really, but it was defined previously. That's a vector field. It happens to be, looks like they're all pointing in more or less the same direction. Our unit tangent vectors, those are those guys that point along the direction of the curve. And at each point along the curve, we're going to take a dot product of a red vector and a blue vector, getting a number. When the two vectors are orthogonal, as they would be like about where my cursor is now, you'll get a 0. When the red vector and the blue vector point in more or less the same direction as they would, whoops, I really didn't mean to move that again. Sorry, put it in a new position too. When they're pointing in the same direction, you'll get positive numbers. And when they're pointing opposite to one another, as they are like right around here, you'll get negative numbers. Those will get subtracted. That's just like the integrand is going below the x-axis there, so it's negative area as you do your integration. Okay, I think they have a nice example of this, but actually before we pass to the example, there are just a ton of ways of writing the thing we're trying to compute, and you're just going to need to be able to recognize them. I'll try to explain the connections between these different ways of talking about our path integral or line integral of the vector field. The first one right there is most straightforward. We're just saying as you move around the curve, you dot the field with the tangent vector. This is all done with respect to arc length. This next one is not so bad because all they're doing is kind of expanding what the pieces are. Uh, F is F, but T, that's R prime over the length of R prime. And ds is our speed times dt. So this is a reasonable way to express it too. Um, you see how there's an r prime of t and an r prime of t, one in the numerator, one in the denominator? Those cancel, and you've got a truly new way to express the work that we would be getting out of this thing, which is the integral of f dot r prime dt. But wait, we're not done. That just explains the first two things on the next line. F dot t ds, sort of where we started. Then F dot r prime dt, that's mostly just moving us to being able to work in t coordinates rather than arc length, which may not even be calculable. But what is this next thing saying? Well, r's derivative is part of this. See the x prime, y prime, and z prime that are in there? Why are those multiplied by things? That's because f had coordinates, had coordinate functions. Um, Now, f wasn't getting its coordinate functions quite this easily, but at a particular time, you'll get x, y, and z coordinates, and you'll feed those into capital F, and you can pull that apart so that f of t is the x coordinate of capital F at time t. G of t is the y coordinate of capital F at time t. This note, I think, is supposed to tell us what's going on. Yeah. When you figure out f at t, what you're really doing is figuring out x of t, y of t, and z of t, and feeding them into the function that gives you that x coordinate for the vector field. It is a pretty reasonable shorthand to write it that way. And you should notice something. This expression looks like a dot product, doesn't it? F, G, H, they're functions of time, sure, but that's the components of a vector. And x prime, y prime, z prime, components of another vector. What are those two vectors? They're the things you're seeing right there. R prime is the one that has the primes on it, and f is the stuff that you extract from the definition of f. Finally, I think finally, um, there's sort of an abbreviation they're adding in here, which is called dr. And it is just a vector made out of the differentials, dx, dy, and dz. So if you understand that as just a way to sort of refer to the three XYZ differentials as one grouping of things that we call dr, then what you're looking at there when you do f dot t ds is writable as f dx plus g dy plus h dz. How come? It's really, I'm taking this in the reverse order for a reason. The reason that this can be done is dx is x prime dt. And we saw x prime dt up here. It was somewhat separated. There's the x prime and the dt's on the end. But just divide both sides by dt and you'll see that it says dx dt is x prime. Yeah, that's just the Leibniz notation for the derivative and the Newton notation for the derivative. And yes, they are indeed equal. But writing it this way is saying the same thing in terms of differentials. Yeah, so that's actually kind of the most compact and in many ways the best way to think or to write your line integral of the vector field. It's just the integral over the curve of f dot dr. All right, there is one final app in this section that I want us to look at. Oh, I've left things turned on. Sorry. Let's turn that off. What we've got now is a picture of a vector field, F. That's the little red arrows. And do remember, those are probably scaled down by some large factor so that they don't run into each other. But you get the idea of this flow, I hope, from the way those red vectors look. We are going to be moving from P to Q along an arc of a circle. And they've specified a bunch of points along with it. Then P1, P2, P3, and Q. Let me just first show us the position vector. You can watch that move along the curve as I go through these 5 points. Back to the beginning. Well, that's fine. What about the tangent vector? That in that position makes sense to me. It's pointing in the direction of the curve. Same thing. But isn't the tangent vector and our position vector orthogonal, provided this is a circle? Yeah. We can also get this thing to draw the function, the vector at each point here. This is the full-size vector as opposed to the little ones, the scaled down ones that are used to visualize it. So the tiny little red vector there is actually this long. And what is the dot product of our tangential direction with F? See, T and F are both big old vectors. They're about a unit long, and they're pointing in the same direction. That's going to be a 1 that we'll add to things right there. And I don't know if that 1 right there is a label or no, I think that's from the y-axis. If we move over to P1, now F's vector, the vector of the field is that way. The tangent vector is this way. They're kind of in the same direction, but not 100%. So that's not going to be as large of a thing. The size of the two vectors are similar to what they were when we were at P1. P. Yeah, maybe one of them's a little shorter too. But the direction between them is different. So you're going to get a smaller dot product. I think at the next position, you're going to get 0. Oh, worse. Here you're going to get a negative value because these guys are not, they're no longer pointing in the same direction. When you do a dot product, the angle between them is greater than 90 degrees. You'll get a negative number. The place I'm wondering why P2 isn't right about here, where the tangential direction and the vector field vector would be perpendicular to each other, because there you'd get a 0. So we had 1, we had a smaller number than 1, 0 right around here, then this number seems to be negative, and it gets worse. At P3, the vectors are pointing in opposite directions. So that's as negative as you're going to get. And at Q, it's not quite as bad because they are pointing against one another, but they're not completely antipodal. Yeah. So, by looking at this thing at P, P1, P2, P3, and Q, you can think of it as a Riemann sum, but what we really want to do is a smooth integral that goes along this entire arc. All right, well, that's about where I want to stop with this stuff for today, mostly because it's about midnight here in Boston, and I'm getting tired, and I need to write up a little worksheet for you guys to do tomorrow as well. But maybe before I sign off entirely, let me just point out there's a bunch of exercises in 17.2 excuse me, examples in 17.2. And I don't want to go through them all, but I would like you guys to look at example number 5 and see if you can parse it, you understand what's going on in this. Um, a lot of the force fields that you run into in real situations, gravity and electricity, not so much magnetism, but anyway, gravity and electricity obey an inverse square law. And so this is having us think about, well, what kind of integrals we get out of looking at those kinds of force fields that get weaker as the square of your distance from the center of the field. So yeah, so take a look at that. Um, it's got a pretty reasonable setup to read. Excuse me, and the solution is given in pretty good detail. So you should try to run through that. And with that, I will say good night.